Welcome to Brain Vision.
So we want to find, for part A, the radius of the path. So we can say that the radius of the path will simply be equal to the mass times the velocity divided by the absolute value of the charge times the magnitude of the magnetic field. This is going to be equal to 6.64 times 10 to the negative 27th kilograms times the velocity of 35,600 meters per second. This will be divided by 2 times 1.6 times 10 to the negative 19th coulombs, and then times the magnitude of the magnetic field, 1.10 teslas. And so we find that the radius is going to be 6.73 times 10 to the negative 4th, and this will be meters. This will be the radius of the path. So this will be your answer for part A. And then for part B, they're asking us to find the direction of the magnetic force. So for a very short time interval, the displacement of the particle is in the direction of the velocity. So we can say that for a short delta t, we can say that the displacement of the particle is in the direction of the velocity. So we can say that the magnetic force is going to be we can say that the magnetic force is going to be always perpendicular to the velocity doing no work. So V is constant. So essentially what it's saying is that the magnetic force, because the magnetic force is always perpendicular to the velocity, it has no bearing on the velocity. No component of the magnetic force is changing the velocity, and thus there is no acceleration. The magnetic force is doing no work on the particle. Therefore, again, there's no acceleration, and velocity is constant, even though there's a magnetic force acting on the particle. That magnetic force, however, is is always perpendicular to velocity, so it's acting in a completely different direction. So again, velocity is constant for part B. That is the end of the solution. Thank you for watching.